Hello, everybody. My name is Eric Williams, and I want to welcome you all to our webinar series that's proudly hosted by the Concrete Preservation Alliance. This series had covered a number of topics regarding advanced assessments. We've been exploring real-world investigation techniques for post-tension voids, corrosion conditions, condition assessments, post-disaster testing, and we're going to get into unknown foundations today. If you missed any of the first three sessions from this series, you can always access all of our resources on the website, wesavestructures.com/webinars. Today, we are wrapping up the series in our final session, Uncovering the Unknown, Investigating Hidden Structural Conditions. This session is going to explore how advanced techniques like ground penetrating radar, impact echo, pulse velocity, and half-cell potential testing can reveal critical information about unknown foundations and substructure conditions. These tools are transforming how we investigate structures, especially when blueprints are missing and we have very high risks. So if you are new to the Concrete Preservation Alliance, welcome. We are a coalition that is dedicated to promoting best practices in concrete repair and preservation throughout the world. Our mission is to offer free, accessible, and non-commercialized education, sharing practical knowledge from professionals in the field to support long-term durability and sustainable infrastructure. We extend our sincere thank you to all of our members and supporters worldwide, those who collaborate, and the dedication they make to the Concrete Preservation Alliance and the educational events like this helps us make it possible. So if you've missed any of our previous or past sessions, you can always go on our website, wesavestructures.info, where you'll find not only the presentation slides, but videos of past sessions that we've held in our webinar series. And also when you're there, and if you have the ability to stay and click around a little bit, we also have an environmental impact calculator. This is a free tool that helps you estimate the environmental benefits of repairing and replacing concrete structures that you can use and help make decision-making to help preserve concrete structures in the future. So before we begin, one of the things that really makes these a success is participation from the audience. And we love to get your questions and find out more about how we can help you in the future. So in the chat, please include your first and last name, and we will be giving away a $100 Amazon gift card to the person who submits the best question. And our speaker, Bill, will be able to choose that winner at the end. So please get those in, and we'll address some of those at the end. And if we don't get to all of them, we'll make sure we'll follow up with you afterwards. So with that being said, and speaking of Bill, this is Bill Horn. He's going to be our presenter today. Bill is the Vice President at NDT Division, VCS Engineering. Bill is a professional engineer with over 30 years of experience and has been with NDT for the past 8 years. So we really appreciate Bill and the time he's taken out of his busy day to educate us a little bit. So Bill, I'll throw it over to you. And appreciate, I hope everyone enjoys.
Great, Eric, thank you. You can hear me okay, correct?
Yes, sir, you sound great.
Fantastic. Well, thank you very much. Looking forward to sharing some of our testing experience. I've got a little outline here. We're going to get into understanding what some of the assessment techniques really are and the valuable information we can gain from them. These techniques like impact echo, pulse velocity testing, ground penetrating radar, there's different frequencies that give us different valuable information. Half-cell corrosion potential testing to understand where the active corrosion is going on. A little more traditional geophysical test methods, seismic refraction gives us some general soil profiles and layers of a site, maybe before some of the borings are put in. Ultrasonic thickness testing for metal, whether it's a section loss of flanges or webs. We do a lot of anchor bolt testing as well with that technology. I've got a bunch of case studies to share with everybody, and you can see where these different test methods help investigate and quantify infrastructure. And of course, we'll have time for questions at the end. So with the effects of deterioration, it's a little bit late by the time we can visibly see the cover concrete spalled off and the steel starting to corrode, starting to lose some section loss on the reinforcing bars, and loss of strength, that corrosion is going to continue on. The elements, that concrete cover is gone, and that's design purpose is to protect the steel from the elements. So impact echo, concrete cores help us also. They're a little bit more of a destructive methodology, but they add a lot of valuable information. Ultrasonic thickness for anchor bolts, even steel testing if we need to get a piece of steel and check the tensile strength. But we can't really come up with a good repair solution unless we understand the cause of the deterioration. And like I said, sampling, cores, chloride concentration from powder samples are all very valuable. With concrete cores, we can slice them, polish them, put them up under an electron microscope, and do petrographic analysis and really see the concrete matrix, any additives, the air-void ratio, when it was poured, and this is valid on existing concrete. Or looking for the presence of carbonation. That's becoming more of a concern and a valid corrosion mechanism. But if we can go back in time with some of these, visual inspection and observation is kind of at the tail end of the time spectrum. It's a little too late to do much of anything. But if we can go back in time with half cell readings, ground penetrating radar impact echo, we can recognize where the deterioration is and correct it for a reduced cost, hopefully with less resources. Good example would be a delamination survey. I've sounded a lot of concrete with an S-wing hammer, and my ear is only so good. So my ear would tell me the white hatched area sounds delaminated, but actually the delamination extends into the yellow area. I just couldn't pick that up with my ear, but our testing equipment can pick up where that is delaminated. But the extent of repair quantity should probably go back to the red, because that's where the active corrosion is going on in the concrete and working on the rebar. It's hot, it's cooking, and that can be quantified with a test technique. So the removal limit should probably go back to the red, but if you just sounded it with a hammer, you might end up with a white hatched area. Now, rust never sleeps. There's a good classic rock connection. In 1979, Neil Young and Crazy Horse said it in an album that is a classic for sure. But for condition assessments of concrete, we want to understand how energy waves move through solid concrete or through soil or through rock. And we're recording the velocity information of how these sound waves go through, and if they get reflected and refracted off of anomalies, or maybe don't even go through a crack. And we're also measuring the frequency data, which is based on the amplitude of these energy waves. These are compressional waves and shear waves. But a rule of thumb is if the energy wave is faster, if the velocity is higher, it's likely going through a stronger material. So here's an example of how acoustic waves might bounce off of an obstruction. This happens to be a cantilevered little obstruction. These energy waves bounce back and forth. They also bounce into each other. So it's really the first arrival of these energy waves that give us the most information. And we collect this information once we excite it with an energy source with sensors. The best analogy I can come up with is dropping a pebble in a pond of water, and we are measuring the velocity of the rings that radiate out from where that pebble went plop. Our sensors are touching the water, or in this case, they are touching the concrete surface. Sensor 1, channel 2, channel 3, we record this information on the first arrivals, and that's the surface wave that travels on the surface of the concrete. There's a reflected wave that goes vertically, kind of like the depth sounder or fish finder in my pond of water example, and that goes down to the bottom of the concrete and gets reflected back up, and it actually gets trapped. And that energy oscillates between the boundary conditions of, say, a concrete slab. And we can determine the thickness. That frequency can be directly related to the thickness of an element. Now, we're following two existing ASTM procedures. Pulse velocity, remember that's the surface wave. That's in the concrete side of the spec, 597. And impact echo is also in the concrete side of ASTM, and that's 1383. So if there's micro cracking within the concrete, that's going to slow the velocity down between channel 2 and channel 3, for instance. And then maybe when it gets over to channel 3 and 4, there's an anomaly or a debonded, delaminated area, and that's going to further impact the velocities and the integrity of the signal. So the velocity information helps us get the compressive strength, and the echo or frequency information helps us determine the dimension and the presence of delaminations. On the right-hand side of that screen, that frequency without any delaminations would oscillate maybe at a 9.5-inch thick frequency. So the deck is 9.5 inches thick. And it's 9.5, 9.5, and all of a sudden it changes to 3.5. And in this certain area, that thickness frequency is 3.5 or 4 inches. Well, if the rebar cover is 3.5 or 4 inches, that's a conclusive way to determine that in this area there is corrosion and there is debonding and delamination of the existing rebar within the concrete. Here's a picture of our equipment that we make. On the right is our portable energy source. It fires a special steel bearing. It's an air gun. It's hooked up to a tank of compressed nitrogen. So unlike my hand, every time I hit concrete with an S-wing hammer, the amount of energy that I'm swinging that with changes from hit to hit. That's not the case with the gun. Every time we pull the trigger, we are inducing the same amount of energy into the concrete surface every time. And on the left-hand side are our sensors. This happens to be a 4-sensor array, channel 1, 2, 3, and 4. Closest to the gun, channel 1 and 2 are about 6 inches apart, 2 and 3 are about 12 inches apart, and 3 and 4 are about 12 inches apart. So over 30-inch lineal distance, every time we pull the trigger on the gun, we get velocity information and frequency information. And then we move it, and we go up and down or do a continuous line all across, go up 2 or 3 feet, do another continuous line, and we can do a complete survey of the whole surface of a concrete beam or a concrete wall or a deck or a column or whatever we happen to be testing at the time. Other components of our instrumentation, we do have special steel bearings that are one-time use only, and we collect those. The gun that we have there, the upper right is the 4-sensor array. Lower left is a computer, data collection equipment that's mounted in a Pelican case. We ship this all over the country, all over the world. And we also assess crack depths with this equipment. And there's a relationship to the distance from the energy source and or the distance from the sensor, the receiver, relative to the depth of the crack. And sometimes we will hold the energy source in the same location and move the sensor away 6 inches, 12 inches, 18 inches, or hold the receiver constant and move the energy source away, again, 6 inches, 12 inches, 18. And we record this information and get some general depths of cracks. A lot of times our crack depths are reported, say, in the 0 to 3 inch range, the 3 to 6 inch range, or the greater than 6 inch, which does help compared to looking at a crack, wondering how deep it goes. It does give you a little bit more information. The pulse velocity data, the top 5 on the left, those blue lines, that's the nice amplitude dissipation that we're looking for good, competent concrete. And then the lower ones, they're not as uniform as the top 5. And there is some delaminations or some cracking or some debonding that is going on. And we can quantify that over that shot area and zero in on where the hidden anomalies are. On the right is a curve that we've developed to equate the velocity, compressional wave velocity and shear wave velocity to compressive strength. And we generally have our values that are calculated within about 500 psi if there was to be a core that was extracted from the same area and broken in the lab according to ASTM 39 and 42. Our readings would be within about 500 psi. You're taking that core out of its element, so let's remember that. When we record information on a beam or a column or a deck, we're doing it in situ and more representative of the internal stresses that might be acting on the midpoint of the beam or in the deck or in the bay of the deck between the girders. So I might argue our number is a little more representative as opposed to you take a core out of its element, ship it to a lab and trim it and break it, but they do correlate very, very well. Now the other discussions were surface testing. If we have access to both sides of a column in this case, or a wall or an abutment or a pier, we can do tomographic imaging, where we are getting a perimeter image based on velocity profiles that are going crisscross all over the place at different elevations and from the north and the south and the east and the west on this round column. And we create a series of velocity profiles, generate a perimeter image, and then we slice that image. And internally, we can determine the condition of the concrete. It's very similar to what the medical community does with a CAT scan imaging technique of maybe our brain or our heart or our kidney. Once they have the perimeter image, then there's slicing that they do. We do the same thing. It takes a little bit more time in the field to collect all the data. It takes a little bit more time in the office to analyze all the data, but is an effective way to get the internal core strength of some concrete areas if we're looking at preserving and rehabilitation. Or if there's new concrete, like in this closure pour, there was precast members on the bottom, precast members, that Y section on top going to the superstructure, but a closure pour with an awful lot of reinforcing. And there was some questions of whether there was some consolidation issues within that closure pour. And we were asked to come in. We had 2 barges, 2 man lifts, and we did tomographic imaging and testing of that closure pour, and then we sliced it. And sure enough, one example slice is slice E. The blue, which is the majority of the image, is supposed to be about 7,000 PSI, 15,000 feet per second. But 3 clicks over and 4 clicks down, it's not blue. It's not 7,000 PSI. It is closer to 3,000 or 4,000 PSI. So the strength of the concrete has dropped off. Now, it's not a void. It's not a crumpled up, coffee cup or something like that, but it is not 7,000 PSI. However, we were able to quantify this. It was very isolated in one part of this closure pour, and the engineer and the owner got together and recognized that this was a pretty isolated anomaly, and nobody was really too worried about it. But without our testing, that wouldn't have been known, and we were able to quantify that. Another example of through testing would be the yellow arrows would be the surface testing of a column base, and the 2 red arrows would allow us to test right through that column base where there's plate steel on the end of it, and we don't have access to the part of the grout pad, if you will, that's underneath the column. So we can do surface testing and through testing on that. Now we'll shift gears. We're still using impact echo, pulse velocity, but now we're looking at the length of piles. We need access to the pile, plain and simple, whether it's the top of the pile or the side of the pile, above water or below water. Our equipment is waterproof, but we need to touch the pile. And we measure the velocity. We impact the pile, and that's a timber pile or a steel pile or a concrete pile. We impact it. We record the velocity in that particular pile from our sensors. We also record the 2-way travel time as that energy wave gets reflected off the tip of the pile or potentially reflected off some sort of a defect or anomaly partway down. Maybe they pulled the cans too quickly, or there was some groundwater around when the caissons were installed. So these types of anomalies do creep into them, and we can determine them. And then we calculate the length, right? We have velocity, we have time, we calculate the length. Works very well. Another application for this same impact echo pulse velocity equipment would be locating voids in post-tension tendon ducts. The steel strands are pulled very tight in these hollow segmental sections of usually large signature bridges. It's a very common design technique. And then the strands are tight, they're anchored, and then the conduit, the duct is then filled with grout. Problem is, it doesn't always get filled with grout. There was some high chloride grout that was on the market a few years ago. That's now off, but some of that is still in some of these tendon ducts. Or maybe the QA/QC of the grouting process was just not as good as it needed to be, and there are voids. And if there are voids, those tendon strands start to corrode. And we can locate those voids in that upper right image. If it's solid and grouted, our energy will go right through it. If there's a void in there, there's water, there's air, there's grout that never set up like peanut butter, the energy wave is going to go around the duct. The frequency is going to change, the thickness reading is going to be different, and we can determine where those voids are. Now, this same application can be used in soil with the assistance of some soil borings, some cased borings. And these borings probably need to be within about 20 or 30 feet of each other, maybe in a triangle position configuration, or maybe a square rectangular configuration. And we can do cross-hole testing or down-hole testing and quantify the soil in between the borings. By, again, adjusting our energy sources and holding our receivers at known locations, or keeping our receivers fixed and adjusting our energy source deeper, 5 feet, 10 feet, 15 feet. So picking up a lot of the crossing wave paths for that. So now we're going to turn the page and get a better understanding of another tool in our tool belt, which is ground penetrating radar. So while the other impact echo pulse velocity was a kind of a seismic energy, this is an electromagnetic energy that comes out of the antenna and gets reflected off material that is more conductive than the surrounding configuration. So rebar is much more conductive in a concrete reinforced member, and a water line is much more conductive down 4, 5, 6 feet in soil. And when we cross over these anomalies, we can pick up the location of them as well as the depth of them. Now, our frequency range in the civil engineering applications, if we're in the soils, we're down 100 megahertz is as low, 200 megahertz, 400 megahertz is our workhorse subsurface antenna. 900 megahertz is kind of a mid-range crossover frequency, but that's the range for low frequency. For high frequency, we're in the minis. Some of them are self-contained. They're about the size of an iron on the right image up top, and that's 1500 megahertz. That's great for locating rebar within concrete. So maybe we're looking for conduits underneath the sidewalk, or maybe we're looking for rebar in the concrete. And the data looks like individual parabolas as far as the reinforcing is concerned. We know what the cover depth would be. We know what the spacing would be. And we are just going north to south on these data lines of collecting data, or east and west, trying to pick up various information. Again, here's the high frequency GPR data, the parabolas, the spacing, the cover depth. We put it on poles to reach the undersides of bridges. And access is usually the biggest challenge for us. And as I mentioned, the low frequency, that antenna gets bigger. Each one of these is connected to a computer for data storage and analysis. But on the left, the 900, this is good for bridge load ratings. This will penetrate through the asphalt wearing surface, the concrete deck, and identify, in this case, a concrete arch and how much soil is on the barrel of the arch. So we'll do a top-down assessment from the road. Technician's got her waders on, and she'll go down in the stream bed and do a bottom-up assessment of the concrete arch, and we'll be able to put the whole picture together for the load rating that's required with the bridge inspections. In the middle is the 400 megahertz. That's our workhorse for locating utilities, sinkholes, whatever the case may be. And that orange antenna is getting a little bit bigger as the frequency goes down. And on the right image is the 200 megahertz antenna. That's even bigger. It has a little more penetration, but you lose resolution. The deeper you get information, the less clear it usually is. And sometimes we may use 2 or 3 different antennas to get the full picture of the subsurface conditions. So again, often one antenna is not sufficient. Example of the results for some soil, the large plot on the left is a bedrock profile. That's down about 50 inches, so 4 or 5 feet. Continuous line of the rock. This happened to be associated with some cell tower investigations. Those guide wires that come down from the cell tower, what are they anchored in? Are they on just a spread footing, or are they doweled into rock? That makes a big difference as far as the load rating of the cell tower when additional antennas are going to be installed. The upper right is a foundation, buried foundation. It has some discolorations, and we know the depth and the location of that. And the lower right is a pipe reflection. Again, that's that parabolic shape, and we're crossing over it, and we get some general ideas of the soil conditions. Happens to be a clay layer associated with that. One other tool we've got is corrosion potential survey. So it really measures the voltage between the rebar and the concrete surface, and that's the active corrosion cell that corrodes the rebar. This is just measuring that potential difference in volts before the concrete has spalled off. Again, catching it earlier in time and hopefully reducing the repair and rehabilitation costs. So we have to make a positive connection to the rebar. It has to be black steel. Epoxy coated does not work. And then we're just touching the surface of the concrete with a copper sulfate, kind of a wet sponge, and it measures the voltage. And we do maybe a 2-foot grid or a 1-foot grid over an area, and we can determine where the active corrosion is. That sliding colored scale in the lower left, if it's brown, if it's more negative than minus 350 millivolts, then that is highly active corrosive areas. If it's less negative than minus 350, then it's less likely to be corrosive. It would be the passive part of the steel and not need to worry about corrosion. Less targeted areas for the repair parts. So we're touching it, and then first we'll locate it with a GPR, great at finding rebar, make a positive connection. We got a little lead sinker that kind of gets smashed in there, and then we drill in and make that connection in the middle, and then we just touch the surface. This happens to be a large concrete tank, and I think we have maybe a 2-foot grid or a 2.5-foot grid, and then we can map out the whole wall or wherever we have readings on for what's the corrosion potential for that particular concrete member. Seismic refraction survey. Now this is a little bit more in the geophysical side of life, and this is a little bit bigger bang than a BB gun. And this is a 10-gauge black powder shotgun shell, kind of a size gun as we call it. And that gets stuck into the ground by a foot or two. We have our geophones or hydrophones that are suspended on the surface, and we're measuring the velocities, the direct energy wave velocities and the refracted energy wave velocities on these hydrophones or geophones. Maybe they're spaced every 10 feet, and we can get a good indication on the general soil profile, but a continuous profile, not just a boring. A boring is a point location. It's just like a core in concrete. We're getting a profile all the way across our 300 or 400 foot line of geophones in the rays. On the left is some hydrophones in the water. I think this was a scour vulnerability application for bridges. If we can determine the bedrock is shallow, then we can make an assumption that the abutment or pier is completely founded on shallow bedrock, and the scour vulnerability changes considerably. The middle is the size gun that's kind of stuck through our blasting mat, about ready to release the safety and hit the firing pin with a hammer. All the equipment's portable. The lower right is a individual geophone. It's basically a magnet suspended by a spring and picks up very, very faint vibrations. It is all timed and wired into our recording devices that is keyed off of the size gun at time 0 when we have a big bang. We'll do the size gun at the 0 station, at the 400-foot station, and then maybe in the middle or a couple of 50-foot increments. And then we're done with that 400-foot line. We can pick that up and move it. So again, this is very effective, very portable, and good to collect general soil profile information, not detailed, but general prior to a subsurface investigation. You might be able to cut down the number of borings, or you might be able to locate them in a particular area. So this is an example of some knee-high water where a barge or a track-mounted drill rig would have been really challenging to get in there. And we were able to use our hydrophones and come up with a complete rock profile, which was the objective as they were sizing the span lengths for a new bridge across a river. And we got about 1,400 feet in 2 days. I've got a case study that will expand upon this. The one important thing here is to recognize that shear wave velocity is a valid way to determine the strength of rock. So is RQD, how many pieces of rock do you have in an NX core? Or if there's one big piece of rock in a core, you can pull that out, trim it, and break it, compressive strength, just like you would concrete, or you can get the shear wave velocity. Caterpillar to this day uses shear wave velocity in a lot of their specs for rock rip abilities. And 3-to-1 ratio. If we're going down 100 feet, we need 300 feet of hydrophones or geophones on the surface. So if we're only going down 30, 40 feet, we can probably get away with a 100-foot line of geophones. But if we want 150 feet down, we better maybe have a 400-foot line of arrays to document all that. And there's the example of the bridge. The hypotenuse is the new alignment of the bridge. And we got 1,400 lineal feet. Continuous rock profile proved that the rock was a weathered shale capable of the bearing capacities that the spread footings were going to produce on it. And it was between 14 and I think 18 or 19 feet down, continuous with a profile. So that was valuable information. We did this in 2 days. You'd take an awful lot of borings to do 1,400 lineal feet in a lot more than 2 days. Ultrasonic thickness testing. This is still a reflection method of a different frequency of a little pulse. And we want to grind down the top of the anchor bolt, which is the example in the middle. Put a little dab of goop on it, and we can record the length of the anchor bolt or the thickness of a web or a flange on a steel member. Interesting with anchor bolts that in Florida, there's now, I believe, a trend to document anchor bolt condition generally for all these high mast lighting structures or cantilevered sign structures. And then after a hurricane, go back and check them, make sure that they haven't been stressed, they haven't been fractured, and keep an eye out for corrosion and section loss that could come in and impact the diameter of those bolts. This equipment, by the way, needs to be calibrated every day. And once a year, we send the UT testing equipment into the manufacturer for calibrations. So we'll shift past. That's what's in our tool belt for investigation. I want to show where we can apply this in various case studies. We've got some fire damage concrete, some post-flood investigations. As-built conditions are not the same as design conditions. We all know that, and documenting the as-builts are important. Talked about post-tension tendon ducts, got some other examples of honeycombing and consolidation. We do some pipe testing, and I'll wrap up with some underwater applications. But as far as fire damage is concerned, a particular bridge, the superstructure was lost to the fire. The question was the abutment impacted? Was the strength of the concrete impacted by the high temperatures? So we did some coring and we did some testing and pulled some rebar samples out, checked the tensile strength for that, did our impact echo pulse velocity testing in the lower part of the abutment, in the middle part of the abutment, and in the upper part of the abutment. Like I said, took some cores, put this all together, and determined that really the surface of the abutment was what was damaged. Once you get outside of 3 or 4 inches, the strength comes back, and the integrity of the overall abutment, once you're deeper than 8, 9 inches, it has not been compromised. So we were able to validate the coring results with our impact echo testing and preserve and salvage those abutments. On the opposite side of fire is freeze thaw, and this is a buttress associated with a dam where the freeze thaw of this buttress is 12 to 18 inches deep on the right image there on the right. So the question was, what's the competency of the core strength of this buttress? How strong is the concrete in the middle of the buttress or the pier? And we had some access provided for us on one test buttress. That's about 8 to 9 feet across. So it's pretty large. And we did our through testing. So we had sensors on the left side of the buttress and energy source on the right side of the buttress and went right through it. We also correlated that with some horizontal cores that were 4, 5, 6 feet long horizontally into that. And then we broke them at certain thickness depths in there, and the results correlated very well. This happens to be a little weaker concrete, one of the surface slices that we did, but we slice it deeper beyond 12 inches to 24 inches, and everything turns green and blue, and the core strength of that concrete was fine to accommodate the new loadings of some new equipment that was coming into the hydro facility, and that was the whole objective of checking the condition of these buttresses. Another application of a bridge pier here, the outside, pretty bad. Shotcrete already failed. Cover concrete, gone. What's the core strength of the concrete? That's what the client wanted to know. Can it be salvaged? Can we just encase this pier, chip away the outside stuff, put some dowels in there, and just overpour it by 6-8 inches? So we did the through testing. On the left side with the 3 guys on a barge, that's where the energy source is. On the right side, we've got our sensor, the 1 guy in the little skiff, and he's picking up those readings, and we're going right through that. And we determined that the overall strength, compressive strength of the internal concrete, the core strength was over 5,000 PSI. The outside was 900 PSI, or we didn't even get readings in some areas because it was so deteriorated. So the solution was there's 4 other piers. We can preserve this concrete. There's no reason to demo this out and build another pier. It was all on piles with pile cap covered with riprap. So the scour vulnerability was very good on this particular bridge. So through testing confirmed preservation was the option. Post-flood inspection, sometimes there's sediment transport or the soil gets washed out away from a sidewalk, which is a concern for pedestrians, or a parking lane if you're parking right adjacent to some coastal areas. So the GPR, the low frequency GPR, penetrates through the sidewalk and picks up the voids underneath it. And on the right-hand image, we can identify where there's broken layers, where there's voids, where there's high moisture, and identify areas for stabilization. Maybe there's some grouting that needs to be done to fill those voids. Another application is a dam spillway. So on the lower part, we've got our velocity information, compressive strengths. 5,000 is green, 1,000 is brown. So mostly green, which is good, but there is some areas that are weak and deteriorated. Overlay that with the delamination survey where the rebar is debonded from the concrete. That's the red and the white image in the lower right. We can lay those 2 over each other and see where the weak concrete strength correlates to the delaminated areas, and usually they correlate very closely. In the upper right, we used a couple different low frequency GPR antennas, went through the spillway and determined there were some voids and tried to quantify the depth of those voids for filling that void with grout. Good to have some sort of a quantity estimate when we're looking at that. Another larger investigation, there did a couple of test areas of a large spillway for us. Wanted to kind of validate our testing methodology. We got the condition of the slab, and some limited plans say, well, the slab might be on rock and it might be on rubble. It was on rock in places, it was on rubble in places, in some places it was on nothing because the rubble had washed away. So we were able to, like I said, power wash a couple of different test areas, do our testing. So the condition of the slab and the presence of voids under the slab were the objective for that one. A little bit on scour, we have a lot of storms. They seem to be more frequent and bigger every year. And when in terms of a bridge crossing a river, there's an obstruction, like on the right image, where the hydraulic turbulence can actually start to erode or scour away the riverbed material, making the bridge pier or the bridge abutment very unstable. So quantifying the foundation embedments or the length of the piles or the location and depth of bedrock is very valuable when we're looking at the scour vulnerability of unknown foundations. We have to quantify it. We can't just leave it as an unknown or a U or an old rating of a 6 in the bridge inspection world. That's not allowed anymore. If it's unknown, assume it's pretty bad and it's going to be scour critical, and there's other plans of actions that are required. Or quantify it. Determine that it's embedded 6 feet, quantify that it's on rock, or that the piles are not unknown. The piles are embedded 45 feet. Now we can use that information to assign a more appropriate scour vulnerability rating. That's the NBIS item 113 rating, where the foundation configuration is key to assigning that rating. Another example is a riser on a dam where there was no plans available, so we did some investigation and quantified the condition of the concrete and the presence of rebar. Some of it was underwater. We put our equipment in the hands of divers and came away with a good picture of what was in place there. Really interesting case study here. Voided precast box beams. These are very common. There is a large cutout of maybe styrofoam by design in the center of these beams, but there's expected to be maybe 5 or 6 inches of concrete around the top, the sides, and the bottom of the beam. That's a little challenge for consolidation for the fabricators. So looking from the bottom up with the GPR, like we are in both of these images, we can determine, did they get that 5.5 inches of concrete thickness on the bottom of the beam before the void? Or if they didn't, gee, does that mean that the pre-stressing is not embedded? Or does that mean that the rebar around that 5.5 inches is not encased in concrete? The answer is yes. And a bore scope investigation confirmed there were big voids and the pre-stressing strands were not embedded. A little hard to load rate that one. And the pictorial, or the image that we provided from the GPR looking up, the green line is the bottom of the beam, the red line is the end of the concrete. So it's pretty thin in a couple areas, a long way from 5.5 inches. So more voids in a voided box beam than anybody really wanted. For the corrosion potential survey, the base of these piers were getting splashed with salty water every time a car went by. So it was the lower 3 or 4 or 5 feet that had much higher corrosion, active corrosion, than above 5 feet because it wasn't in the splash zone. So we were able to identify that, quantify, target the deteriorated areas, and that was used in a corrective repair application to mitigate, counteract that corrosion. There was some sacrificial zinc anodes, I think, that went in there as part of the column forming process, and that protected and preserved that structure. Transit tunnels, a lot of those in the big metropolitan cities. This particular one had 2 duct banks to the right and left of those red arrows. They were going to pull out all the old electrical cables and wanted to make sure the integrity of the duct bank wasn't so bad that it was going to collapse and have concrete rubble that fouled the rails. So we tested, I think it was every 20 feet, and we did about 4,000 lineal feet in 2 nights worth of work and determined the integrity of this duct bank was fine. This was not compromised, it was not deteriorating, it was not falling apart, and a good representative area every 20 feet for 4,000 lineal feet proved that for the client. I talked about pile lengths. Here's some examples where we're getting the pile lengths of sheet pile. I think there was a dredging operation that was planned. There was no installation depths of the sheet, so we wanted to know how deep they were. And often with sheet pile, there is accompanying tiebacks and anchors, so we could locate them with a GPR and they could excavate up, and then we could quantify what the anchors are for the load rating analysis. Again, pile length testing, we've got a concrete pile, it has to be exposed, so we're doing some excavation or shoring as needed to get it to the piles. Sometimes it's below pile cap and the shoring is very complex. Timber piles in the middle, we use the ratchet strap with our sensors, and steel piles on the right happens to be a marine. Question was, at what point does the pile change to a concrete filled pile? And we could determine that as well. Post-tension tendons, once they get the asphalt off, we find the tendon ducts with GPR, we test the tendon ducts with impact echo, and document the voids with a bore scope. And these tendon strands are already showing some signs of corrosion. That's a big void. That should be full. Both of them should be full to the top, and they're not. And that's able to quantify that. Another hydro example was we first tested some of the individual concrete, and then there was these steel liners that were going in these draft tubes, and they were going to grout the annulus of the liner. So there's a, I don't know, 3/4 of an inch or an inch thick gap between the metal and the concrete. And did they get the grout all in there? Or did it need to be topped off? The amplitude signal over on the right, the top one, that's the dissipating signal we want with time. The middle one is kind of full, but it's not really bonded quite well. And the bottom one is not full. There's a void there. That one needed to be topped off a little bit more. Consolidation, take the forms down, you see that, nobody's happy. I want to know, well, how far does that honeycombing go into the concrete? This is brand new concrete that we just poured and paid for. Or on the right horizontal cold joint. Maybe it's July, we're waiting for a concrete truck for an hour or two, or stuck in traffic, and is that concrete bonded, upper concrete bonded to the lower concrete? Well, if it is bonded, then the energy waves will cross over. If it's not, they won't. Another QA/QC application for GPR was a new cast-in-place concrete tube about 11 feet in diameter, supposed to be 12 inches thick. And the 12 o'clock high position of that pipe is probably the most challenging area to make sure you got a full 12-inch thick pipe wall. And somebody approached us, the contractor said, "Hey, can GPR tell us how thick this is? We're supposed to drill a hole through this every 150 feet for 3 miles. And can we cut that down with GPR?" The answer was yes. So we got the 900 onto a shaft and used a little tension spring action hinge to keep it flush, and just drove the cart right down the rail system and did 3 miles in about 2 days. So very effective. Results were great. Did some validation testing where it was a little less than 11.5 inches and correlated it just perfectly. QA/QC of grout injection. We're often asked to quantify a concrete member before epoxy injection is going in to repair it, the cracks, and then do it again after the cracks have been repaired. So on the left, on the right-hand side, the red images or the weaker concrete, they all went away after the grouting was done. So this is a conclusive way to determine that it was effective to get all the grout done. Pipe testing, pre-stressed concrete cylindrical pipe, that's very common in municipal water distribution and collection systems. And there's obviously tanks that are associated with that. And when that amplitude changes, there could be some debonding of how PCCP is put together, or we measure the thickness of the pipe wall, or if the pre-stressing strands have failed, that section of pipe is no longer in compression, and some of the frequencies and velocities change with that. Again, we're recording the compressive wave velocities, the shear wave, the thickness of all these things from the inside or from the out. Large diameter pipes during an outage, we work inside, or just with shoring, uncover them. Municipal pipe here, we try to identify where the good ones are in green and where the bad ones are in red. Well, whether it's thinning of the pipe wall due to hydrogen sulfide, or debonding of a layer, or loss of compression in the pipe. And to wrap it up here, we also have worked with ASI Marine to mount our Impact Echo equipment onto their ROVs. Don't think anybody in the world can do an underwater condition assessment with an ROV. And we're very proud of our relationship and our success with that. For outfall pipes, or for some areas of hydroelectric plants where you just don't want to put divers, we're looking to get the concrete strength ultimately, or the dimension or thickness of a pipe, and apply that. On the right, we've got our sensors on the top of the ROV that extends up, the energy source and the sensors, and on the lower image on the right, we've got it on the front of the ROV. It extends out, have a little brush to get some of the algae off, and we can get a lot of information. As far as through testing, we've got the ROV could be on the water side, impact the face of a dam, and we could have some rope access support or other access on the dry side and go right through the dam. We're in discussions with a number of different clients and hydro facilities to do this through testing of a dam. But as a summary, we're kind of focused on selecting the right investigation tool to diagnose the cause and come up with an effective rehabilitation strategy. And Impact Echo, GPR, and half cell potential, those are right at the forefront. A couple of cores along with them for photography or chloride concentration if we're salting the roads. That's an effective way to determine the condition of any piece of concrete. And if it's competent, let's preserve it. We don't need to demo it out, spend more carbon to put it in a landfill, and spend more carbon to build something new. But we need to know that. If it is compromised and past its service life, then let's know that for sure, not get into big change orders and run into some challenges later on. So Eric, I think we did okay on time. Do we have any questions here today?
Yes. Let me see. Sorry, I'm just I'm adjusting my screen a little bit. Give me one moment. And yeah, really nice job, Bill. Appreciate everything there. So a couple of questions that came in quite a bit. So the first one, was there ever an effort to utilize this technology, or a modified version anyway, to help identify the development of sinkholes in major highways?
Yes, but usually as a reactive measure, when there is a sinkhole reported or presence, what is the extent of that? And a lot of times, some of the bigger sinkholes that, swallow up lakes and neighborhoods are different than maybe a small scale sinkhole where there's just a simple drain, 12-inch drain line connected to some grates and scuppers, and that's been compromised. So now the water's not inside the pipe going to where it's supposed to go. It's on the outside and it's pulling the sand with it, and it's raining and the pipe's flowing and more sand is coming out of a broken pipe. So yes, but normally on a reactive basis. When you're doing a new road, you hope you've got competent compaction and try to avoid the macro sinkholes. So it does apply to both.
Excellent. And this one I know comes up quite a bit, and it's the limit of what the GPR or the impact echo can do through a wearing surface. So asphalt wearing surface, polyurethane waterproofing membrane, things like that.
Yep. No, that's a tough one. And we can collect data, impact echo pulse velocity data on a concrete slab through asphalt if a couple conditions apply. It can't be a hot July day because that asphalt is just too soft. We need it to ring. So if it's cold, if it's relatively thin of an overlay, and that's less than 2 inches, and it's got to be bonded. If the asphalt is not bonded to the concrete, all I'm going to be able to say is the asphalt's not bonded to the concrete. And there can't be a felt membrane. Sometimes the bridges have a waterproofing, I don't know, 1/4 inch, 1/2 inch thick felt membrane. That's a bond breaker. That's an air void, if you will, layer. If it's just the tar waterproofing that's been slapped on, or some of the sheets that go down, we can do that. Or we take the asphalt off in selected areas, or look at from the bottom up. We get an underbridge inspection unit. If there's a lot of asphalt, we'll just look at the deck in between the girders from the bottom up, and we can assess that as well. So good question. Did I get all the components of that, Eric? Or?
Yeah, no, I think you did very well on that. And keeping with some of the extents of what it can do and what it can't do. Someone is asking if pulse velocity can determine the extent of the corrosion on the rebars itself from the outside.
Well, pulse velocity impact echo cannot. It can identify where a thickness frequency has changed from the thickness of a 9-inch deck to maybe 3.5 inch, which is the depth of the concrete cover. For corrosion on the rebar, that's really where the half-cell corrosion potential test is very complementary to quantifying where the delaminations are. They usually go hand in hand. There's some microcracking, water's getting in there, and it's starting the corrosion cycle. So impact echo, not corrosion directly, but delamination. But where we have that, let's do the half-cell corrosion potential and really quantify what the active corrosion is. Good questions today, Eric.
Nice. Yeah, absolutely. So another one, and I think this happens quite a bit when you're doing your pulse velocity testing on the post-tensioning ducts. And the question came in is, how easy or difficult is it to differentiate between the rebar that may be around those ducts and the ducts themselves?
That is a difficult question. And depending, the rebar configuration is one criteria that can inhibit the effectiveness of our readings. To locate the tendon duct. So the real art is finding the duct. We can shoot through and around the rebar consistently enough, but if there's a lot of reinforcing, we might not be able to see the tendon duct there. The other thing with tendon ducts, sometimes maybe in a central web of a hollow stem section, they may be stacked up like bowling pins because they dip and dive. They have some high points and low points. And if there's two stacked up like a bowling pin, we might be able to see there's a void, but we might not know which one the void is in. So the tendon ducts kind of need to be single file for us. They need to be a little less than hopefully 15 to 18 inches embedded. And we need to get a straight shot at them. If they're up in the haunched corner, for instance, right, where there's sometimes a 45-degree angle in these upper or lower corners, I don't have a plumb surface to reflect off of. So that central web, single file, perfect. In the floor or ceiling, single file, perfect. Up in the haunch corners or stacked up together, there are limitations for our detecting grout voids.
Oh, very, very good. Appreciate that, Bill. And something that actually it gets brought up a lot too is when you're using your GPR on concrete, is the GPR scanning able to detect concrete delaminations within a slab?
The signal gets a little fuzzy. You might have suspect areas of delamination with GPR, but the conclusive way to know if it's delaminated and the limits of the delamination are to do the impact echo and that reflected. That's where that thickness frequency is going to change. Thickness of the member we're traveling through is going to change, and that'll be a conclusive way to know that it's delaminated. Might be a fuzzy signal, but if there's air voids around the corrosion, now we're not getting accurate results from the GPR. It might tip us off, but it's not a conclusive way to determine delamination and debonding.
Very good. And this one comes up, and I thought this was a pretty interesting question, is different post-tensioning and probably parking garages or buildings and the paper wrap systems. So one of the questions that came up is, are you able to perform a half cell potential test on a paper wrap PT system? Are you able to get that continuity through the paper sheathing?
No, I think that layer, I've been exposed to a couple instances there, and that layer does impede our ability. It's kind of like a bond breaker where there's an air gap. Sometimes our signal gets stopped. So we might be able to look at it from a different configuration, or maybe there's an isolated opening that could be done to look in and try to investigate in a suspect area. So.
Okay, no, that's good. And then with GPR, are you able to locate reinforcing and footings, cover size, etc., or are we able to determine where the bottom of the footing is, the depth? And an example would be the depth of the footing.
Yeah, certainly finding rebar if we're on the footing. It's a little much to ask the electromagnetic energy to go through the soil into the concrete footing, bounce off the rebar, come back out of the footing, and go back up all the way through the soil column. So we excavate it, expose the top of the footing, and yes, we can pinpoint the top layer of steel, the bottom layer of steel. If you want to know the bar diameter, GPR or a packometer is not going to conclusively tell you it's a number 5 bar. It might say, well, we think it's 4, 5, or 6. On a load rating analysis, a big difference between a number 4, a number 5, and a number 6. So if you want a bar diameter, we'll find where the longitudinal transverse bars cross, we'll chip them, we'll expose them in an opening, measure them with a caliper, take a picture, and patch it up with a high-strength grout. But as far as the footing dimension, the thickness of the footing, absolutely. GPR, if there's not too much steel in there for the electromagnetic energy to go through and come back up, we can get a dimension, footing thickness that way. And certainly the impact echo reflected area, that thickness frequency, we can confirm what the GPR tells you as far as thickness. And one thing to mention with GPR, Eric, is sometimes one antenna is not going to give you all the information. Sometimes you get some shallow information with one antenna, some mid-depth information, and then the deeper information with a different antenna. It's really the experience. We've got 30 years of experience looking at the data that allows that type of investigation that's very complex to be successful and add value to the engineers and ultimately to the owner of the asset that we're investigating.
Excellent. Yeah, no, that's very good on that one. And, Bill, this is one that came through, and I don't know if I've been asked this one yet. I thought it was a pretty good one. So, you gave a couple of examples of through testing with your pulse velocity and the impact echo, right? And
Yep.
they tend to be on thicker columns or on vertical. But what about doing it on elevated horizontal surfaces? And this person used like a deck as an example. Would you test from the top, typically be sufficient? Or have you done some through testing? And if so, what's like the minimum that you would do through testing on thickness of something?
Right. Good question. First, let me clarify the penetration from the surface testing, right? If it's 7, 8, 9 inches, we can probably get get an assessment of the full thickness of that slab from one side or the other, because that's what we can penetrate from the surface. Now, if it's thicker than that, and maybe it's 2 or 3 feet thick, we come across large, heavily reinforced areas all the time, and with access to both sides. The trick with the through testing is we need to know where we are, right? We need to have a very accurate X, Y, and Z coordinate system, because if we're off a little bit, we would attribute that to a longer travel path, or is that weaker concrete? So again, we take painstaking time in laying out a grid system to know exactly where we are on the left side of that pier, for instance, or that closure pour, and the right side of those members. If you're on the bottom of a floor and the top of, or a slab and the top of a slab, we could still do that layout from columns through, or, drains or pipes or what have you, cutouts in the slab. But the real effort would be laying out a very accurate X, Y, Z coordinate system with any through testing tomography project.
Good. Thank you. Yeah, no, I think that's good. And another one that came in, and I think this comes up a little bit for you too as well, Bill, is when you're doing the testing of your precast cylinder pipe, are you able to test, is your test able to quantify the wire breaks of the pre-stressing string?
That's a very good question. The answer is yes, we can quantify where that pipe section is no longer in compression. And let's remember, those pre-stressing strands are on the outside and they compress the pipe and give it its strength. Now, there's a certain frequency and velocity associated with that. So if the wires are broken or compromised in a certain section, we would be able to say, look, this section of pipe over this 4-foot area or 10-foot area or whatever it is not in compression based on our results. I can't say that, oh, there's 12 wires that are broken. So it's more of a, I can quantify it, and from a macro sense that it is not in compression, but sometimes they want to know, well, is there 8 wire breaks or 10 wire breaks? And that's, I just can't do that with our testing, either from the outside or the inside. We do work with some other testing partners. Sometimes we're working together and can complement each other with some blind spots that others have that we don't have, and some other areas that can be quantified where those wire breaks exist.
No, I think a good explanation. Appreciate that. And another one, and you may have touched on it a little bit ago, but just to follow up, when your GPR and you're using your GPR and you're using your signal and it's going down through a void, does it continue finding voids for the full depth of the member, or does it get caught up in that void? How does that GPR react when you go over a void like that?
Yeah, the air void does absorb. Air is more conductive, and it soaks up that energy. So we have less penetration when we're going through an air void. It still may go through, like compacted gravel under some asphalt, roadways or what have you. But where there is significant voiding, that one particular antenna may be limited. And as I said before, that's where maybe 2 or 3 different antennas with our experience and knowledge can help stack that together. So yes, air voids are a problem for GPR, and depending on the extent of them and the depth of them, we can successfully get some limited information if we look at it in a different way.
Excellent. And this one I have not heard yet before, and we would understand if there's some proprietary knowledge that cannot be shared, but I thought this was an interesting question for you, Bill. Has AI been used to interpret the data of NDT scan, or excuse me, in the interpretation of NDT scan data? If not, is there a timeline that may start doing that?
That's a very good question. The answer is yes. We have been working for a number of years with artificial intelligence we have so much data of velocity information correlated to compressive strength of concrete. And we've used AI programs to extrapolate that. And now, rather than just recording information, knowing it's good data to be analyzed later, we have the ability in some instances to know what that compressive strength is right on site. So a very exciting AI application to so many parts of our lives, but in the velocity, not so much in the length and the dimensions yet, but in the compressive strength directly from the velocity information. Yes, we are in it, and we intend to stay with it because it is a game changer for us.
That's great. Well, I know we're getting close on time, or we're a little over on time, but I have just one or two more I was going to run past you, Bill, if you're okay with that.
Sure. Bring them on.
So another one that came through was for the impact echo and the pulse velocity. Can it be used for deck thickness on new bridges with, like, say, complex geometry and deflections that may not be matching the analysis? So this person gave an example of like a variable haunch. You know, have you ever used it for something like that?
Yeah, that we need a reflective surface, right? We need to bounce that energy wave off the backside of the column or the backside of the pier stem or the bottom of the slab or footing. So up in haunches or corbels, right? Some decorative architecture and things like that. It's a little hard to get a clear reflective bounce back of that signal for us. So there is some limitations, but big flat areas, no problem. That's where we thrive.
And I'm going to wrap it up on this one with you, Bill, but I thought this was a good one because we talk so much about concrete and steel and things like that, but somebody asked about timber. So they asked, do any of these tests have application in testing mass timber for loose strength and rot?
Yes, in terms of pile lengths. We use the pile as a waveguide, so we're going kind of with the grain on the length of the tree, and we can get the length of timber piles from that. GPR does not work in wood. Impact echo does not work in wood for a condition assessment. I think from my bridge inspection days, there's really no substitute from an awl to determine penetration, thickness, a little ice pick, if you will, and quantify the rot that way. You can take little plugs and cores, I know, of timber and look at it, but the only application that we really have here is pile length assessment of timber piles. And again, Eric, we have to touch the side of the pile or the top of the pile.
Excellent. Well, thank you for all that, Bill. I think really great questions and appreciate everything from the audience. I think Bill's going to have his work cut out for him trying to decide what he thought or who he thought gave the most interesting questions. So thank you
for that.
Great
questions. Thank you, everybody, for great questions.
So with that, we're going to wrap up. But if your question did not get answered by Bill live here on the air, we will make sure he gets copies of all those and he will be in touch to follow up. So really appreciate that. And if you found today's session valuable and you want to keep the momentum going for you and your team, VCS Engineering and NDT Division are running a new educational presentation program. The program explores key challenges and practical solutions in assessment and rehabilitation. So feel free to reach out to Bill or Vector Corrosion Technologies for scheduling something like that immediately. As for our seminar or our webinar here, we will be releasing the details of our next Concrete Preservation Alliance webinar very soon. So please keep an eye out for that in your inboxes, or you can check back at the WeSaveStructures.info website. So if you have any follow-up questions for Bill, please feel free to reach out to him directly at the contact info provided here. And just a reminder, everything, including the PDH credit link, will be shared with you by 4 o'clock Central Time tomorrow. So again, that wraps up not only our webinar for today, but our webinar series. So I know there's a lot of you out there who have joined multiple sessions and multiple webinars. I can't thank you enough for giving us that time, and hopefully this series about condition assessments has been valuable. And we look forward to seeing you at future series. And I'll let everyone get back on with their day, and let's go out there and save some structures. Thank you, everybody.
Thank you very much.